Okay students, welcome to Darasa Online, and today we are going to study physics. I'm Cyprian Mgina, a physics teacher, and it will take us to a topic of atomic physics, to the subtopic of nuclear physics. This is the second part. I do hope you have enjoyed the first part, and in our next part we are just going to look at the nuclear mass, the binding energy, stable, unstable nucleus, and the radioactive isotopes, or what we call radioisotopes. Okay, first of all, we really needed to go back and look what Einstein did in 1905. In 1905, Mr. Einstein had developed a particular relationship. He was able to show that there is a relationship between mass and energy, that the change of a mass have an implication to the energy which is produced, and therefore he was able to obtain a very famous expression to show that the energy produced could just be related with the product of the change in mass times the speed of light squared, where c is the speed of light, which is equal to 3 times 10 power 8 meters per second, and m is the change of mass. So that whenever you take the product of the two, you are going to get the energy produced, or the energy which you are just going to get. And this is what we call the energy mass interchange. And this was developed by Einstein in 1905. Now, through this particular expression, we could just be able to see, for example, if you are having 1 gram, let's say, of a mass, of a substance, that the energy which might be produced due to the change of a mass by a 1 gram, this will just be equal to, that particular energy, this will just be equal to the mass which is equal to that particular gram. Or if I take it so straight to a kilogram, then this is equal to 10 power 3 of a kilogram. So it will be equal to 10 power 3 of a kilogram times the speed of a light, which is 3 times 10 power 8. And we take this to be squared. And we can be able to get that particular energy in terms of joules. That particular energy in terms of joules, of which we could just be able to find that this will just be equal to, so we are going to get 9 times 10 power minus 13 joules. So the energy created due to a change of a mass of a gram will just be equal to this much. Will just be equal to this much. And this is what Einstein did. And actually, in electronics and in electronics and in nuclear physics, really we can just be able to, we are measuring the energy in terms of what we call electron volt, such that 1 electron volt is just equal to 1.6 times 10 power negative 19 joule. So this is 1 electron volt. And if I need to get, let's say, 1 mega electron volt, then this is equal to 1.6 times 10 power minus 19. So we multiply by 10 power 6. So we're going to get 1.6 times 10 power minus 13 joules. So this is 1 mega electron volt. 1 mega electron volt will just be equal to this much. Now these are the expressions which can really help us later whenever we are just going to look some other forms of energy. Those other forms of energy can just be measured in terms of what we call a unified atomic mass. Unified atomic mass. That is another unit where we could just be able to measure the energy by having an implication of the mass and the energy relationship which had been obtained very early or just by Mr. Einstein. Okay, students, another form of energy is is what we call a unified atomic mass unit. Unified atomic mass unit. This is abbreviated with U. And the unified atomic mass unit is another way we could just be able to have the energy mass relationship, whereby we could have a definition of what we call a unified atomic mass unit. Now, the definition of a unified atomic mass unit, we define this as 1/12 of the mass of carbon 12. That energy which can just be produced taking 1/12 of the mass of carbon 12. And we can just be able to try to calculate this. We can be able to calculate this. 1 mole of a carbon contains 6.02 times 10 power 23 times 10 power 23 moles. And our carbon is a monatomic gas, such that 1 mole of a carbon contains 6.02 times 10 power 23 atoms. Remember, this number comes from the Avogadro's constant. And if I'm going to take a carbon 12, or one atom, let's say of a carbon, one atom, let's say of a carbon, of carbon 12, will be having the mass of 1 atom. So it means that I will have just to establish that particular mass by just taking 12 divided by 6.02 times 10 power 23. Then this is for a single atom. This is for a single atom, and this is what we call this actually will click to a 12 gram of such kind of an atom. And therefore, if I need now to determine a unified atomic mass unit, then I will have just to take 1 U, then I'll just have to take this much to divide by 12. I'll be able to get a unified atomic mass unit of a carbon. So that if I'm taking 12 over 6.02 times 10 power 23 power 23, if the whole of this I divide by 12, then I'm just going to get 1 U, or one unified atomic mass unit. So that 1 U can just be computed. But if I'm going to take that much, then actually it's just be equal to, will just be equal to 1.6611 times 10 times 10 power negative 24. But remember, this is for a gram. But if I go and look for a kilogram, then it means that I'll have just again to divide by 10 power 3. Then I'll be talking about a unified atomic mass by having a reference of this 1 atom to not to a 12 gram, but I'll be converting that 12 gram into a kilogram, so that this much then we'll have just again to multiply with 10 power negative 20 power negative 3, so that this will be equal to 1.6611 times 10 power negative 27. So this is 1 U could just be equated. We are talking in terms of a kilogram, as long as I have already divided or changed this gram into a kilogram. So 1 U in terms of a mass will just be equal to that much. Okay, students, now we are going back and be able to look to what I've already mentioned previously, that we are measuring the energy in terms of electron volt. In electronics, or in nuclear energy, we are measuring our energy in electron volt. And 1 electron volt is just equal to 1.6 times 10 power negative 19 joules. So that if I'm talking 1 mega electron volt, then it is 1.6 times 10 power minus 19. I multiply by 10 power 6. So I'm going to get 1.6 times 10 power minus 13 joules. This is 1 mega electron volt. But as we have already seen from the Einstein formula, that the change in energy is just equal to the change in mass times the speed, the square of the speed of the light. So that the change of mass of 1 kilogram. So if I'm taking here to be equal to a kilogram, 1 kilogram, then multiply by the speed of light, which is 3 times 10 power 8 squared, we'll be able to get the energy there, the energy which will be produced whenever we are having a 1 kilogram change of mass. So that this will just be equal to 9 times 10 power 16. The change in energy will just be equal to 9 times 10 power 16 for the change of mass of 1 kilogram. Now we need just now to look the relationship between a unified atomic mass and the actual energy in terms of electron volt could just be obtained. So that if I'm talking about a 1 unified atomic mass unit, then I need now to multiply 1.6611 times 10 power negative 27 kilogram. We multiply this with the energy that can just be changed by a kilogram mass, and this is just equal to 9 times 10 power 16. So we divide this with the 1 mega electron volt, which is equal to this much. That is 1.6 times 10 power negative 13 joules. And the whole of this will be equated, or we are just going to get an expression of a 1 unit be equal to a certain mega electron volt. And we can be able to compute this. That here I'm having 1.66. So here we are going to have about 900 and 34.36. We are taking up to some several decimal places. But actually, if we really compute by taking, if you just terminate the rest of the other decimal places, you really end up having equal to 931 mega electron volt. And approximately, that's why they are saying this is as an approximately. And actually, this is just equal to 1 unified atomic mass unit. And this is the value which we actually be using whenever we are looking the interchange of energy from the mass and the actual energy which can just be produced. Okay, students, now let us go and look at the second part of what we call the binding energy. The binding energy. The binding energy is the energy which is really keeping all of the nucleons in the nucleus of any particular atom together. Whenever I'm talking about the nucleons, I'm talking about protons and neutrons as particles which make the nucleus of an atom. So there we are going to get what we call the nucleons. The nucleons are composed by protons. The nucleons are composed by neutrons. And whenever they are existing together in a nucleus, as a nucleus, they have got a particular mass. Now, the energy or the work which can just be done to separate these particular nucleons so that they can be completely separated. Whenever they are completely separated, will really be, whenever I'm looking the mass of these particular separated nucleons and the mass whenever they are existing together, the two masses will be different. That if I'm taking, let's say, if I'm taking this to be the protons and this to be the neutrons, and this to be the neutrons, this to be the protons, this to be the neutrons, this to be the protons, whatever. Now, if they are all forming the nucleus of an atom, so whenever they are completely separated, that I could be having some several protons there and some several neutrons there, several of them, and each one will be having its own mass. So the total mass, when they are completely separated, actually is bigger than the mass whenever all of them they do exist together. Now the difference in mass have an implication of a particular energy which keeps them all together as a nucleus of an atom. And this is what we call the binding energy. And this particular binding energy can as well be determined or computed for any particular atom of any particular element. And we can just be able to see this the way we can just be able to solve. For example, let us just look a very simple example here. Okay, for example, let us just look at the binding energy, which can just give us a very good example. Let us just take, for example, of a helium. A helium is just like an alpha particle. A helium is just like an alpha particle with two protons and two neutrons, which are found there at the nucleus. And as a nucleus, the unified mass of the nucleus of a helium, the nucleus of a helium have a unified mass of 2.0015 U. But the unified mass of a proton, which is just like that of a proton, the unified mass of a proton is just equal to 1.007 U, unified atomic mass. But for a neutron, which is just equal to 10, this is just equal to 1.00, for a neutron 1.0087 U. So these are the unified mass of the constituents or of the nucleons. Those particles contained at the nucleus are the nucleons, and those are the protons and neutrons. So we can try to look now and be able to see what will just be the difference. As long as the proton, there are two at the nucleus, so we could be able to look the total mass whenever they are completely separated. So we are having some two protons. Plus two neutrons. We are just going to look what will just be the mass. So here we are taking 2 times the mass of protons, which is just equal to 1.007. We add the two neutrons, which is equal to 2 times 1.0087. And this is just going to give us, here we'll just be having, you're just going to have a 2.014, and here will just be equal to, if we multiply by 2, here will be having 4 7 1 0 2 point that much, and we can add up to get into the total unified mass of the 4 nucleons whenever they are completely separated. So this will be equal to 2.014. We add plus 2.0174, and we are going to get 4.0314 unified atomic mass. These for the nucleons when they are completely separated. And now we need just to look or compare its unified atomic mass whenever they do exist as a nucleus. So here we look and compare with this one here and see which one is bigger. You see that whenever they are completely separated, they are having bigger value than whenever they do exist as a nucleus all together, as a nucleus of a helium. So we take the difference. This particular difference will have an implication of the binding energy. So whenever we take for the difference, whenever we take for the difference here, then this will just be having what we call, will have an implication of a binding energy which can just be calculated. And so here we are taking the difference. So here we are taking the nucleus of the helium is not 2.0015. It is 4.0015. So we really need now just to compare whenever the nucleons are completely separated and whenever they do exist together as a nucleus. So look here, whenever they are completely separated, it is 4.0314. But whenever they are having as a nucleus, it is 4.0015. So this is bigger than that. So the difference will give us the difference will give us the difference in terms of the unified atomic mass unit, which have an implication to the binding energy, the energy which keeps the nucleons all together. So we take the difference now. So taking the difference, here we are taking 4.0314 minus 4.0015. We are going to get this in terms of the unified atomic mass unit. And we're going to get 0.0, we're going to get 0.0299, the unified atomic mass unit. Now, this unified atomic mass unit could be converted and to see what kind of the energy in terms of electron volt could really holding those nucleons of the helium all together. And as long as I know one unified atomic mass unit is equal to 931 mega electron volt, then having this much, that is 0.0299, can just be calculated. So actually we need just to multiply there. Okay, we need just to multiply there, which will just be equal to 27.8369, or rather approximately to be equal to 27.84 mega electron volt. And this is the energy which is really holding or keeping the nucleons of the helium together. And that is what we call the binding energy for the helium nucleus. Okay, students, let's go and look another thing about stable and unstable nucleus. Stable and unstable nucleus. Stable and unstable nucleus. Unstable nucleus will happen whenever the sum of the product that are just going to be produced, its unified atomic mass unit, are really less than the present nucleus of the a mother nucleus of, let's say, of a radioactive sample, so that that particular sample will just be able to disintegrate, because its mass is really bigger as compared to the mass of what is going to be resulted after it have just disintegrated. So that particular situation will make that particular nucleus to be unstable, and the whole of that particular process will go on. That particular nucleus will continue to disintegrate, and whenever the mass of the disintegrated particles is really bigger than the mother nucleus, then is when the mother nucleus becomes stable. Then let us just look by an example of a calculation. For example, let us take a polonium. So a polonium-210 with 86 disintegrates by producing an alpha particle, that is a helium nucleus. So it means that what is going to be produced will just be a lead. Will just be a lead of 206 to 82 plus a helium. So this will just be our reaction equation of a polonium. By emitting an alpha particle, then a lead is going to be produced, and we are really having such kind of an expression. And now let us just look the unified atomic mass unit. The unified atomic mass unit of a polonium, this is just equal to 209.982 unified atomic mass. But for a lead, this is just equal to 205.969 atomic mass unit. And for an alpha particle, that is a helium particle, then this will just be equal to 4.004 atomic mass unit. Now, what we're going to do here is just to look and be able to, and finally we can be able to see if this polonium is stable, is it stable or unstable nucleus, by having by looking now the atomic mass unit to the products which are just going to be produced during disintegration. So let us just look for this particular case. Let's look whenever they are completely separated. Let's just look whenever they are completely separated. Whenever they are completely separated, we just have one atom of a lead with one atom of a helium, so that we just have to add 205 for a lead, 0.969 plus for a single atom of a helium, which is 4.004, and this will just be giving us 209.973 atomic mass unit. This is for the product. But for the polonium itself, it is of this much. Now we need just to compare between this and that. You could just be able to find that this one is really bigger than the products that are just going to be produced by having such kind of a reaction or disintegration, whereby an alpha particle is being released. And therefore, you will be able to find that from what I've already said previously, the atomic mass unit of the mother nucleus is really bigger as compared to the sum total of the unified atomic mass of the products. And if that happens, it means that this particular mother nucleus is unstable. So we are having a polonium for this particular case to be unstable nucleus. And whenever this is just being produced, there is a release of energy. So the energy will be released at that particular case, and to make the whole equation be stable. And we can be able to determine that particular energy which can just be released in terms of mega electron volt. But for this case, we're having a polonium to be unstable. Now, I can be able to take you to another expression whereby you could be able to find that the mother nucleus could be having a unified atomic mass unit less than its product. And if that happens, then it makes the mother nucleus there to be stable. The mother nucleus there to be stable. And if the mother nucleus is stable, it means that the energy for that, say for the second case, is the energy which has to be supplied to make that particular nucleus, or make that particular nucleus be able to release that particular products in that particular equation. So that will just be the case for a stable nucleus. For this particular example, we are having a polonium here to be unstable, and that's why there is an energy Q which is released in that particular equation, and which can just be calculated, and we can be able to obtain it in terms of mega electron volt. Okay, let us now just go and look the radioactive isotopes. Let's just go and look the radioactive isotopes, or what we call radioisotopes. The radioactive isotopes. The radioactive isotopes are the isotopes which are radioactive. That means that they could be able to release alpha, beta, and gamma rays spontaneously, but their half-life are really very short. And these particular rays which are emitted can have so many uses in our today's technology. And that's why these radioisotopes can just found to have so many uses in the field of medicine, in the field of industry, as well as in research areas. So if we're just going to look, let's say, into a medicine, the radioisotopes are used for in diagnosing various diseases, and it can as well be used to treat some cancer. For example, an iodine radioisotope can be used to treat the thyroid cancer. And we could have so many radioisotopes which can be used for some other uses in a treatment. So medically, we will just be able to find that the radioisotopes have got so many uses, diagnosing some diseases to a patient, in treatment of cancer, various cancers, for various types of cancers. That is for a medicine. We can as well be able to find the uses of radioisotopes in industries. In industries, we could just be able to find that the radioisotopes can just be used in estimating, let's say, the thickness of a particular material. Just like even the thickness of a paper. They can just be used, let's say, to estimate the compactness of the rod, tarmac rod, whatever. So the radioisotopes can as well be helpful to those who are constructing roads to estimate the compactness of the soil, okay, whenever they are constructing road, just like that. And you could just be able to find that in industry, these particular radioisotopes have so many uses. There are so many uses, but there are several of them. Those are just a few to mention. But we could also have some other uses of radioisotopes in research areas. In research areas. And the radioisotopes can as well be used in research areas. For example, whenever they just need to, for example, in agriculture, it's widely used whenever they are trying to produce some good seeds which could be able to produce some, which can be able to make well in production. Let's say there are some seeds like for maize or whatever. These particular radioisotopes are really very helpful in their research. It's very difficult, let's say, to explain here how it's just going to be used, but they are very helpful in research areas. Okay, these are just a few areas where the radioisotopes can just be used. But as long as we just find that there are such kind of an advantage, but there are some hazards of using these radioisotopes. There are some hazards of using these radioisotopes, and we can just be able to mention some few of them. For example, one of the hazards is that these particular radioisotopes, sometimes they can just be able to cause some mutation. That once you are being exposed to such kind of radiations, it can be able to interact with your body cells, and the body cells can try to regenerate some other more cells. It's just like cancerous cells or whatever. So it can be able to cause some mutation. And that is very dangerous. But sometimes this particular radiation, if they just interact with the DNA of your cells, it can be able to make some cells to be cancerous. So it can also lead you, it can be able to lead you to be able to get a cancer. So it can be able to result somebody to have a cancer. Can be able to produce or cause a cancer to somebody whenever he is excessively obtained a very big dosage of radiation produced by the radioisotope. And sometimes for somebody who is having or who have got a particular dose of radiations produced by the radioisotope, could just be able to have a problem of leukemia, that the bone marrow can just really be affected, and hence somebody could just be able to get a leukemia, and later could just be able to get a cancer of a blood, because the bone marrow could just really be affected. These are just a few of the hazards which can as well be obtained whenever we are using the radioisotope. So there is a very big care to be taken, or precautions to be taken whenever we are using these radioisotopes for improving our health, or for a treatment, or for an industry. But yet we should have to take those precautions, but there are so many advantages against those hazards as we are having here. Okay, so students, let's go now to the question I've just prepared for you. The question number 1. The question says, determine the binding energy per nucleon for a chlorine 35 basing on the below chemical reaction. So we are having chlorine 35 plus that energy Q produces the neutron, 18 neutrons and 17 protons. So given that for a chlorine 35, it have 34.98 atomic mass unit U. For a neutron, it's having 1.008665 atomic mass unit, and for proton, we are having 1.007825 atomic mass unit U. So we need now just to determine the binding energy per nucleon for such a chlorine. So here, from that particular equation of a chlorine 35, 17 plus that particular energy, we are having a production of 18 neutrons plus 17 protons. So what I'm going to do is, as I mentioned previously, we need just to look the atomic mass units of the products here and compare with the atomic mass unit of the chlorine there. So for the product, we are having 18 of the atomic mass of neutron. The neutron there is 1.008665. That is for a neutron. So we add the 17 of the proton. The atomic mass unit for a proton is 1.00825. And we need just to compute here to determine the total unified atomic mass unit. So doing that particular calculation, so here is 18.15597 plus 17.133.025. And if we add here, we're going to get 35.288, the unified atomic mass unit. This is for the products, but for the mother nucleus, the chlorine there, that is, remember for the chlorine 35 over 17, this is just equal to 34.9800 atomic mass unit. So we need to compare this one and that one. As I have already said previously, the mother nucleus is having less unified atomic mass than the of a product. So it really makes this particular chlorine to be stable, and that's why it have to be supplied with an energy Q to have such kind of disintegration. And then we need now just to take the difference. We need now just to take the difference, which will really be giving us the binding energy. So the difference here we are taking now for the binding energy. So the binding energy will take us by taking 35.288995 minus 34.9800. So this is going to give us 0.308995 atomic mass unit. So this gives us the difference in terms of the unified atomic mass. Now, if we need to know in terms of the mega electron volt, then we need to multiply by 931. Remember, one unified atomic mass is equal to 931 mega electron volt. So if I multiply this much times 931, so we are going to get 287.6743. These are mega electron volt. So this will just be the actual binding energy. The actual binding energy for a chlorine will just be equal to this much. And our question says we need to determine the binding energy per nucleon. the binding energy per nucleon. Now, the nucleon is composed by protons and the neutrons. And there we are having 18 neutrons and 17 protons. That is, we are having 35 nucleons. So to determine the binding energy per nucleon, so we are just going to take 287.67, we divide it by 35. So if I take the whole of this much, divide 287.67, 4345, divide by 35, then I'm just going to get 8.21. So I'm going to get 8.219 mega electron volt per nucleon. So that is the answer for that particular question. That's the binding energy per nucleon. Okay, 8.219 mega electron volt per nucleon. Okay, students, let us now go for a question which will now be for you to do it as a homework. I'll be able to give you a hint. This question goes like this. Calculate the binding energy per nucleon for the phosphorus 31 to 15, given that the mass of a phosphorus is 30.97376 atomic mass unit U. Neutron, for a neutron is 1.00865 unified atomic mass, and for a proton is 1.00782 unified atomic mass. So you really have to go through the same process. You really have to go through the same process, that you have to look for that particular phosphorus. For that particular phosphorus, the phosphorus is 31 to 15. It means what? It means that with this particular mass number, okay, it means that this is the mass number, atomic number. So it means that the number of protons at the nucleus are 15. The number of protons are 15. And the number of neutrons, now you take the difference between 31 and 15, okay? And this will just be equal to 16 neutrons. And having obtained this, then you go through the same procedure as I did in the first question. That you look, if the atomic mass unit for a neutron is given as well as for a proton, and you know the atomic mass unit for the nucleus of a phosphorus, which is equal to 30.97376, then later you will have just to compare and be able to see, does the proton and the neutrons, whenever they are just existing separately, do they possess a bigger atomic mass unit as compared to whenever they are existing as a nucleus in a phosphorus atom? Having obtained that particular difference, it will give you, or you can be able to calculate the actual binding energy. And as long as you know that particular energy you have just obtained, then as long as you know the number of nucleons, the number of particles contained in the nucleus to be equal to the sum of the protons plus neutrons, which is equal to 31, then you take that particular energy, you divide by the number of nucleons, that will just be the energy per nucleon, as I have done in the first question. So I hope students, you can just be able to do that particular question comfortably. Okay, I believe with this small part which you have just done, really there are a lot of questions. There are a lot of questions which can take you to do many more bigger questions and difficult questions than the one I have just given you as an example here. But as long as you have understood the way to go about using the unified atomic mass unit and having known that particular basic formula of an Einstein, talk about the energy mass relationship, then I believe you can just be able to do a lot of questions with regard to the binding energy and some other related questions. So let's end here, and I believe I can be able to meet you next time to another topic of physics.